This is our second lecture on chapter 13, Solutions. Last time we went over solutions, which were defined as homogeneous mixtures. We looked at solutions of solids and water. We learned about the solubility, the saturation, the electrolyte solutions that can be formed, and solubility versus temperature trend of solids versus water, or solids in water. We also looked at solutions of gases in water, and we looked at different concentration units of solution. We looked at mass percent, and we looked at molarity. Today, we'll actually be learning about the other concentration unit of solutions, which is called molality. We'll also be learning about dilution of solutions, the freezing point depression and boiling point elevation of solutions, and osmosis. So we've seen in lab that solutions are often stored in concentrated forms called stock solutions. But many lab procedures call for less concentrated solutions. So oftentimes our lab coordinator will make the less concentrated solution for us, but sometimes in lab, we may be required to make the less diluted solution ourselves from the stock solution. What we would do to dilute is we would combine a certain amount of the stock solution with water. And to determine the volume of stock solution to use, we would have to use the solution or dilution equation, which is M1V1 equals M2V2. That is M1 times V1 equals M2 times V2. M1 and V1 stand for the molarity and volume of the initial concentrated solution. And M2V2 stands for the molarity and volume of the final diluted solution. The reason that this equation works is because if you were to multiply the molarity with the volume, that would give you the moles of solute. If you're adding water to your solution to dilute it, you are not adding any more moles of solute. So your moles of solute is going to be the same when you multiply molality or molarity times volume of your more concentrated solution, which gives you the moles of solute. And when you multiply M2 times V2, that'll end up giving you the same moles of your solute. Let's look at an example problem dealing with M1V1 equals M2V2. So solution dilution. Here we want to prepare 5 liters of a 1.50 molar KCl solution from a 12.0 molar stock solution of KCl. So we're given that initially our concentrated solution has a molarity of 12.0 molar. So that is our M1. We want to form the concentration of our solution after dilution to be 1.50 molar. So that'll be our M2. How much volume we want of our diluted solution is 5 liters. So that'll be our V2. So now we need to find V1. So we'll use the equation M1V1 equals M2V2. Rearranging to solve for V1 by itself, we would divide M1 over. So we have V1 equals M2V2 over M1. So plugging in what we've distinguished as being our M2, B2, and M1, we see after the canceling of units that our V1 is 0.625 liters. Let's try another example problem. Here we have a 122.0 milliliter sample if a 1.2 molar sucrose solution is diluted to 500 milliliters. What is the molarity of the new diluted solution? Take a few minutes as you try this problem. All right, let's do this together. So we know we're dealing with solution dilution. So we'll be using the equation M1 V1 equals M2 V2. From the information that's given to us, our initial volume is 122.0 milliliters. As long as we use the same units of volume on both sides, we could use milliliters for both of them. We just have to make sure that we're using units of milliliters on both sides. So this way we don't have to convert into liters. Although you can convert both of your volumes into liters as well, but make sure you're consistent. So our V1 is our 122.0 milliliters sample of 1.2 molar sucrose solution. So 1.2 molar is going to be our M1. And that's diluted to a new volume of 500.0 milliliters. So that will be our V2. And we want to solve for the molarity of the diluted solution. So after we have diluted it, what is the molarity? So we're looking for solving for what M2 is equal to. So plugging everything in, we have 1.2 molar for M1 times V1, which again we can leave in units of milliliters as long as we're using volumes on both sides to be in milliliters. And that's equal to M2, which we do not know yet, times V2, which is 500.0 milliliters. So M2 comes out to 0.29 molar. When we're dealing with reactions that involve aqueous reactants and products, it's often convenient to specify the amounts of reactants or products in terms of their volumes and concentrations. So we can use the volume and concentration to calculate the number of moles of those reactants or products. As we said before, when we multiply concentration in molarity times volume, we end up with units of moles. After we end up with units of moles of the reactant or product, we can then use stoichiometric coefficients to convert into another reactant or product using the balanced equation. So for example, if we start off having the volume of, say, reactant A, and we want to solve for the volume of reactant B that is needed to react with reactant A. If we're given the volume of reactant A, and we're also given the molarity of reactant A, multiplying the volume of reactant A with the molarity of reactant A will give us moles of reactant A. Then from the balanced equation, we can look at the stoichiometric coefficients in the balanced equation to look at the mole-to-mole relationship between A and B. And multiplying by this relationship will cancel out moles of A and convert into moles of B. So now we're at this point where we have moles of B. Lastly, we were trying to solve for volume of B. So now we will need to know what the molarity of reactant B is. And by multiplying the moles of B by the molarity of reactant B, we'll cancel out the moles and convert into volume. Notice here, you'll actually have to multiply the moles by the inverse molarity in order to cancel out the moles and have volume be in the numerator. So let's look at an example problem that uses this idea of solving for the volume of one of the components. So our balanced equation is H2SO4 reacts with 2 sodium hydroxides and forms sodium sulfate plus 2 waters. So the question asks, how much of 0.125 molar sodium hydroxide solution do we need to completely neutralize 0.225 liters of 0.175 molar H2SO4 solution? All right, so we're given the volume and the molarity of H2SO4, which is one of our reactants. We're also given the concentration molarity of the other reactant, sodium hydroxide, but we do not know how much volume we need. So we're trying to solve for the volume of sodium hydroxide solution. So we'll start off with the data where we have the volume and molarity given to us. So if we start off with the liters of H2SO4 and multiply that by the molarity of H2SO4, we can then cancel out the liters and we'll end up with just moles of H2SO4. Next, we want to convert from moles of H2SO4 into moles of sodium hydroxide. So for that, we'll need to use the balanced stoichiometric coefficients. We see that there's 1 mole of H2SO4 for every 2 moles of sodium hydroxide. And by multiplying by this relationship, we now cancel out the moles of H2SO4 and convert into moles of sodium hydroxide. Remember that we want to solve for liters of sodium hydroxide. So from the moles of sodium hydroxide, next thing we want to do is we want to cancel out the moles of sodium hydroxide and convert into liters of sodium hydroxide. So for this, we'll need to use the inverse of the molarity so that we have the moles in the denominator and the liters in the numerator. And we end up with 0.630 liters of the sodium hydroxide solution. Let's try another example problem. Here we want to consider the following reaction where we have 2 K3PO4 or 2 moles of K3PO4 reacting with 3 moles of NiCl2, forming 1 mole of Ni3 and 2 PO4 ions. Plus 6 KCl. So what volume of 0.225 molar K3PO4 is necessary to completely react with 134 milliliters of 0.0112 molar NiCl2? Take a minute, try to solve this problem yourself. Refer to the last slide to get you started. All right, let's do this together now. So we're given the volume and the molarity of NiCl2, and we want to convert into the volume of K3PO4, and we're given its molarity. So again, we're given both the volume and molarity of NiCl2, so we'll start there. So first, we need the volume to be in units of liters, which I'm going to go ahead and convert it myself. I know that 134 milliliters is 0.134 liters. But again, you can also just do an extra calculation to determine that. So that is 0.134 liters of the NiCl2 solution. Now we'll multiply this by the molarity of the NiCl2. So there is 0.112 moles of NiCl2 for every 1 liter of the NiCl2 solution. Right now we've canceled out our liters of NiCl2 solution, and we're dealing with moles of NiCl2. Now we can use the balanced equation to convert between moles of NiCl2 to moles of K3PO4. We see from the balanced equation that there will be 3 moles of NiCl2 for every 2 moles of K3PO4. So now we've canceled out our moles of NiCl2. And at this point, we're down to moles of K3PO4. Lastly, we want to convert into volume of K3PO4 solution, not just the moles. So we will now use the molarity of K3PO4. We want the moles to be on bottom, so the moles cancel out. And on top, we want liters of the K3PO4 solution. And the molarity says that we have 0.225 moles of K3PO4 for every 1 liter of the K3PO4 solution. So this now cancels out our moles of K3PO4, and we will be down to units of liters of K3PO4 solution. So our answer comes out to 0.00445 liters of the K3PO4 solution. Now, colligative properties are properties which depend on the number of dissolved solute particles and not on the type of solute particles. So when we add a non-volatile solute, a non-volatile solute is one that does not easily evaporate. When we add a non-volatile solute into a liquid, that ends up extending the temperature range over which the liquid remains a liquid. So we should be familiar with what range water remains a liquid. We know that water in degrees Celsius has a range of 0 degrees Celsius all the way to 100 degrees Celsius, at which it remains in liquid state. However, if we were to add a non-volatile solute into the water, its range would be extended to being a little bit lower than 0.0 degrees Celsius and a little bit higher than 100 degrees Celsius. So overall, with the solute added into it, our temperature range over which water remains liquid would be more than 100 degrees Celsius. So by adding a non-volatile solute, the solution will now have a lower melting point in other words, a lower freezing point, and it'll now have a higher boiling point than the pure liquid by itself. So these effects are called freezing point depression because the lowering of the freezing point, and boiling point elevation because of the higher boiling point. So in automobiles, we use antifreeze not only to prevent the freezing of the coolant within the engine, especially in cold climates, but it also prevents the boiling of the coolant in hot climates. So freezing point depression and boiling point elevation depend only on the number of solute particles in solution and not on the type of solute particles. Again, that's what makes freezing point depression, boiling point elevation colligative properties. For freezing point depression and boiling point elevation, we will now be introducing a new concentration unit of solution. This new concentration unit is called molality, and it's symbolized by a lowercase, normally italicized, m. And molality is equal to your moles of solute over kilograms of solvent. Let's look at example problem 13.8 from your textbook. To calculate the molality of a solution that contains 17.2 grams of ethylene glycol, which is C2H6O2, which is dissolved in 0.500 kilograms of water. So we're given 17.2 grams of our ethylene glycol, which is our solute, and that's dissolved in 0.500 kilograms of H2O, which is our solvent. And we want to find the molality. Again, remember that molality is equal to the moles of your solute over kilograms of your solvent. Again, we said that our solute is C2H6O2, and our solvent is the H2O. So we have grams of our solute, and we can use its molar mass to convert into moles of the solute. So 17.2 grams of ethylene glycol multiplied by its molar mass gives us 0.2771 moles of our ethylene glycol. And we already have kilograms of H2O. So we'll plug in the 0.2771 moles of ethylene glycol over 0.500 kilograms of water, and we end up with 0.554 molal, or molality. Let's try another example problem. We'll do number 1 together, but take a few minutes to try this on your own. Here we want to calculate the molality of each of the solutions. So we're calculating it for the first solution, where we have 0.25 moles of our solute, and we have 0.250 kilograms of our solvent. Let's do this together now. Remember that molality is a lowercase m, which is equal to our moles of your solute over the kilograms of your solvent. So we already have in number 1 the moles of our solute and the kilograms of our solvent. So we can just directly put this into the formula. So 0.25 moles of the solute over 0.250 kilograms of the solvent. And we get that the molality is equal to 1.0 molal. Now the freezing point depression of a non-electrolyte solution is quantified by this equation here, where the change in freezing point, or delta TF, is equal to the molality times K sub F. So delta TF is our change in temperature of the freezing point in degrees Celsius. So that is the change in temperature of the freezing point from the freezing point of the pure solvent. M, lowercase m, is our molality. Lowercase and italicized m is our molality of the solution, which again is in units of moles of solute over kilograms of solvent. And K sub F is our freezing point depression constant for our solvent. Oftentimes in this class, we're dealing with a solvent where the solvent is water. And K sub F for water is 1.86 degrees Celsius times kilograms of your solvent over moles of your solute. Let's look at example 13.9 to calculate the freezing point of a 1.7 molal ethylene glycol solution. So we're given that the molality is 1.7 mol solution, and we're asked to find the freezing point. Remember that we're also given the K sub F constant, and that was in the last slide. So we're trying to solve for the freezing point change. Well, we need to solve for the freezing point change first. So delta TF is equal to molality times K sub F. The molality is 1.7 moles of your solute over kilograms of your solvent. And that's multiplied by K sub F, which is 1.86 degrees Celsius times kilograms of your solvent over moles of your solute. Notice that your moles of solute is both on top and bottom, and your kilograms of solvent is also on top and bottom, so they cancel out. And you end up with units of just degrees Celsius. So your delta TF, or your change in temperature freezing point, is 3.2 degrees Celsius. Remember that we have freezing point depression, not freezing point elevation. We know for pure water, the freezing point is 0.00 degrees Celsius. It is then depressed by adding this ethylene glycol solute. The freezing point depression is now depressed by 3.2 degrees Celsius. That means that now our freezing point is negative 3.2 degrees Celsius. The boiling point elevation of a non-electrolyte solution is quantified similar to the freezing point depression. So for the boiling point elevation of a non-electrolyte solution, its equation is the delta T of the boiling point is equal to the molality times K sub B. Delta T is our change in temperature of the boiling point in degrees Celsius from the boiling point of the pure solvent. M is the molality of the solution, and K sub B is the boiling point elevation constant for our solvent. Again, our solvent is often water. So for water, the K sub B is given to us here, which is 0.512 degrees Celsius times kilograms of solvent over moles of solute. Let's look at an example problem. 13.10 to calculate the boiling point of a 1.7 mol ethylene glycol solution. So in this problem, we're given the molality, which is 1.7 mol, and we're asked to find the boiling point. So this problem will be solved similar to how we solved the problem earlier. So we would want to solve for the delta TB first, and that's equal to the molality times K sub B. We have the molality, and we have K sub B. After the canceling of the units, we end up with just units of degrees Celsius. So delta TB is equal to 0.87 degrees Celsius. Now the problem is asking for the boiling point, not the change in boiling. So we know for water that the boiling point is 100 degrees Celsius. With this ethylene glycol solute added into our water, we now have a boiling point change of 0.87 degrees Celsius. This is called boiling point elevation, which means that the boiling point has now increased. So if it has increased by 0.87 degrees Celsius from 100 degrees Celsius, our new boiling point of this solution is 100.87 degrees Celsius. Let's try the first example problem. That is to calculate the freezing point of a water solution at each concentration. So our concentration that we're looking at for our first problem is 0.85 molal. And we want to solve for the freezing point of the water solution. Take a minute as you try this on your own. Right now, let's do this together. Here we're trying to solve for the freezing point of the water solution. And this is after we've added a non-electrolyte. So this is not just pure water. If it was pure water, it would not be a solution. So this is a non-electrolyte solution where water is our solvent. So the equation we want to use here is that delta TF is equal to the molality times K sub F. K sub F for water was given to us, and here the molality is given to us. So our molality is 0.85 molal times K sub F, which is 1.86 degrees Celsius times kilograms of solvent over moles of solute. Remember that molality is broken down into moles of solute over kilograms of solvent. So the units of molality cancel out with the moles of solute and kilograms of solvent that are in our K sub F. So multiplying these two numbers, we get the delta TF is equal to 1.6 degrees Celsius. Again, this is freezing point, depression, which means now that the freezing point has gotten lower than just the pure solvent by itself. The freezing point of pure water remember that that is 0.0 degrees Celsius. And now it has been depressed by 1.6 degrees Celsius in this new solution. So the freezing point of this non-electrolyte solution is equal to negative 1.6 degrees Celsius. And that will be your final answer. Now, many of us have learned about osmosis in our biology classes. But let's go over it again in chemistry. So in osmosis, that is the flow of a solvent from a less concentrated solution to a more concentrated solution. This occurs when solutions contain a high concentration of solute, which draws a solvent from solutions that contain a lower concentration of solute. If we look at the bottom right picture, what we see is that seawater is a thirsty solution. So on the right side of our picture, we have the intestines. And on the left side is the liquid outside of the intestines. When we drink seawater, inside of our intestines, we now have a highly concentrated sodium chloride solution. In our tissues outside of the intestines, we do have sodium chloride. We do have a sodium chloride solution, but it is much less concentrated. When we end up having a more concentrated solution of sodium chloride in our intestines, what happens is that much of the water outside of the intestines is now pulled into our intestines in order to minimize or to lower the concentration that was inside of the intestines. What ends up happening is that this causes much of the water to now escape your body or to leave your body through the intestines, and now your body is now going through dehydration. In an osmosis cell, water flows through a semi-permeable membrane from a less concentrated solution into a more concentrated solution. And as a result, the fluid will rise on one side of the tube until the weight of the excess fluid creates enough pressure to stop the flow. This pressure that now stops the flow is called the osmotic pressure of the solution. So osmotic pressure is our third colligative property. Remember that colligative properties depend only on the concentration of the solute particles and not on the types of solute particles. So now we have a list of 3 colligative properties that we've learned about. We learned about freezing point depression, boiling point elevation, and osmotic pressure. With osmotic pressure, the more concentrated the solution is, the greater its osmotic pressure will be. With membranes of living cells, they act as semi-permeable membranes. So they allow the flow of water from the less concentrated solution into the more concentrated solution. If we were to put a living cell into seawater, it would lose seawater, or it would lose water through osmosis, and it will become dehydrated. Here we see red blood cells in 3 different solutions of different concentrations. Remember that these membranes of living cells act as semi-permeable membranes, so they allow the transfer of water. And this undergoes osmosis. In figure A, which is shown on the left side here, the solute concentration within the cell and outside of the cell are equal. So although there might be flowing of water in and out of the semi-permeable membrane, the flow of water in and out is equal. So there is no net osmotic flow. And the blood cells will exhibit its typical shape. In figure B, here we have a cell that's placed in pure water. So outside of the cell is pure water. So inside of the cell is our more concentrated area. Because it is more concentrated inside of our cell, some of this water outside of the cell will now flow into inside of the cell. And what ends up happening is our cell ends up swelling up, and eventually it might burst. In figure C, we now have a cell that's placed in a concentrated solution. And because it's so concentrated outside of the cell, water actually flows from inside of the cell out in order to make the solution outside of the cell less concentrated. But what happens with this flow of water that's leaving the cell is that the cell will now distort its normal shape and actually shrink up. So these solutions that have osmotic pressures less than the fluids of the body are called hypoosmotic. And these solutions tend to pump water into the cells. Solutions that have osmotic pressure greater than the body fluids are called hyperosmotic. And these solutions tend to take water outside of the cells and tissues. We can have intravenous solutions that must have osmotic pressure equal to that of the body fluids, and those are called isoosmotic. So when a patient is given an IV in a hospital, the majority of the fluid is usually an isoosmotic saline solution. So that is a solution that contains 0.9 grams of sodium chloride per 100 milliliters of solution. And this concentration would be similar to that of what is already in our body fluids. And with that, we finish chapter 13. Again, a summary of what we learned in our 2 lectures is we learned about solutions, which are homogeneous mixtures. We learned specifically about solutions of solids and water. We learned about the solubility of solids and water, the saturations. We learned about electrolyte solutions versus non-electrolyte solutions, and we learned about solubility and its temperature dependence. We then learned about solutions of gases and water, and then we learned about 3 different concentration units of solutions. We learned about mass percent, molarity, and molality. We then learned about dilutions, or dilution of solutions. We learned about freezing point depression and boiling point elevation, and we learned about osmosis.